What do these things all do? Front, back, and pointer?
Yeah. Oh, left and right.
Okay. I'm going to briefly describe an experience I had in 1982, roughly speaking, when I managed the semiconductor operation here in Fort Collins for HP. I was 26 years old, and I made the mistake of proposing to my boss that we just simply do a radical shrink of integrated circuit processes, thinking that he would assign that to somebody and that person would go off and do it. But he said, okay, you're in charge. So I learned a lot from that experience, most of it somewhat painfully, and I'm going to pass some of that on to you today. I don't think you're going to learn anything dramatically new here, but putting it all in one place may give you some ideas that might help accelerate some of the experimental work in fusion, cold fusion. I have to mention, by the way, when I came here to this conference, I ran into 4 people from my previous life here in Hewlett-Packard in Fort Collins at this conference out of 150 people. What are the chances? And 2 of them were in the IC operation working with me to develop this technology. Okay. So I'm going to cover the program goals for the system we are developing, our initial approach, and the problems that we encountered, and the responses that we did. And it's sort of in the problems, the unexpected problems in our responses that are the learnings that might be applicable for this group. The reason I'm going to go through some of the detail is there's a psychological aspect of when you're running a development program that's important to understand. When you're in the middle of the program, you might not recognize your environment and what you need to change, and those symptoms are something I hope to convey here today so that maybe you'll go, oh, I've seen this movie before. So the program, I've used some literature here that I dug out of a file that I had in my closet that explains what the program is about. So the original program goals were to design, develop, and manufacture a reliable, cost-effective, state-of-the-art processor and memory system for this particular group of HP, and to manufacture that technology. So what it ultimately looks like is the little, okay, let's see if we can make this one work, is this card cage, and it had a bunch of boards that went in there, and what was included in that was a 1-micron double tungsten metal process, 6 VLSI chips, each up to 600,000 transistors, special packaging, and all this was done with 15 IC process engineers and 35 circuit and system designers, and a couple guys to work on the packaging, and 3 test people, which turned out to be very important. The tooling, the hardware design tools we had to develop all this, the computer resources, were less than the resources that are in a current watch, probably way less than the resources that are in a current watch. So you had to be focused. Okay. So I want to introduce some vocabulary terms because they're going to turn out to be important later. The first one is success. You know you've had a success when you meet all the goals and everybody's happy. I found that sometimes success is illusory because you'll meet all the goals only to find out they were the wrong goals. And you'll see an example of that later. The second vocabulary word is failure. That's when you clearly have not met the goals, and you know that you have to change radically because there's no hope. You have to do something different. But the new term here that you might not have dealt with in the past is near success. That's when you think you're making progress, but the gains are illusory. You're not actually getting much closer to the goal, but you slavishly stick to your original plan. That's strategy stagnation. So if you want to learn more about this, and it's not really central to what I'm going to present today, but it might be interesting, all this is presented in some IEEE documents, which might be a little harder to find, or the HP Journal, August 1982, which you can find on the internet. And it's about, I think, about 30 pages that goes through all this, the technology of what we're talking about in some detail. The point today is not so much the technology, but it's why we did what we did and what we learned as we were going along as it relates to accelerating technology development. So in the integrated circuit world, it turns out it's very important to be able to make things smaller. There are a lot of benefits that accrue when you make things smaller. So for example, if you make the line width smaller, the power delay product, which is a figure of merit for the circuit, varies can be as dramatically as L to the line width to the 6th power. Plus you get higher reliability and lower cost. The cost per function goes roughly somewhere between L cubed and L to the 6th. So that explains why every year in the last 50 years there's been a tremendous pressure to reduce the geometry of circuits, and you've all seen the benefits.
Careful of that laser, it's vicious.
Okay, I'll use this one. Thank you. But it turns out that, yes, it has all these benefits. It's not easy to do. So we developed a process, and you can see a cross-section. Again, this is some of the original, probably looks naive, information now. Cross-sections of a first-generation IC process. We did a second generation, and this is the third-generation process. You can see that the whole thing fits in the contact region of one of the previous generation processes. And there were some other things we did to reduce the area this is a single transistor would take up from an old version of a process but with the same geometry as the new version. So this is about a third the size of this, even though they have the same design rules. That turns out to be better, but of course it has its own set of problems. Again, a historical document showing what I presented in my naive thoughts of, okay, here's what we're going to do, boss, to make this happen. And, we understood roughly the kinds of things we needed to do as we scaled this process down 50 to 1 in area. So the previous process was 50 times larger for a given function. And there are a lot of things that we knew we had to do, and then maybe there were some things that we thought we might have to do, and a few things we had to explore. Some of the new things might be hot carry or injection into a transistor. You make a transistor smaller, they tend to degrade over time because the electrons bounce around in places that you don't intend them to be. So fine, we're off. And we had, these are just an example of some of the issues that we expected to face and some of the fixes for those issues. So for example, the first problem was defining 1 micron features. In a microscope, you can barely see 1 micron features, and we had intended to use an electron beam lithography system developed by HP Labs. They were, cast of characters out there working diligently to produce 1 micron lines and spaces with a 1/4 micron 3 sigma alignment tolerance, so layer upon layer would be off no more than a 1/4 micron. We also developed things that even if the tolerance wasn't that good, we could still make the circuit work, and you saw an example of that a few minutes ago. So there's a laundry list of things problems we anticipated and potential solutions to those problems. Now, we were only able to print these, to test these things at first because we didn't have the electron beam system with contact printing, maybe 10 transistors at a time with a optical system. So the problem with that is it allowed us to find generic problems such as hot carrier effects, but it maybe didn't allow us to understand the problem of scaling up from 10 transistors to 500,000 transistors on a chip. And it didn't necessarily allow us to understand interactions between some of these issues up here and our processing technology, which in fact turn out to be the major issues in these development efforts. So again, the deliverables were this IC technology. First IC technology in the world using tungsten metallization. Tungsten has some unique characteristics, but it was difficult to do. Putting together system design for all of these chips, and then building the chips, packaging them, and then fabricating this stuff at significant volume. I should mention that this was not a science project. When I volunteered to do this, the goal is this is the division's product. So if this doesn't work at some point, there's going to be a lot of people not gainfully employed. So the original project was proposed in spring of '76. The original end date was supposed to be 3.5 years later. You can see it's about 5 years later. And now I'm going to tell you why and what we learned. We went through a methodic process to correlate process parameters to output parameters. So this is one of about 50 pages of things that develop design rules. You start off, You start off with, let's say, an error of the resist definition, an error of various other, the etching under that, and so on and so on. That tells you where a certain line is going to appear, best case, worst case, and in between. You combine all that, and it tells you how close, let's say, two contacts can be on your metal mask or something like that. So there's 50 pages of these, all of which you like to, first of all, prove you could do and then verify it happening in real life. Now, when you scale an LSI device, they don't necessarily stay the same in terms of their characteristics. For example, this is a typical MOS large device, and you can see the so-called quadratic behavior where the current, which is what this is a plot of, grows quadratically with a difference between the gate voltage and the threshold voltage. Okay, so that's an ideal device. Our devices look like that. There's short channel effects. You can see as the drain voltage goes up, it conducts current when you wish it wasn't in this case. The point I'm making here is we were able to design we did design our system taking into account these parameters, but our models were not perfect. In fact, there were perfect models, but they're so cumbersome and so speculative that it was better for us to actually just measure devices and interpolate the results. And my point here is going to be later that you don't have to know everything about what you're doing, but you do have to know the important things. And I'll come back to some of those important things that we didn't know in a minute. Another effect is the change in threshold is a function of the gate length of the device. And you can see here, we were operating at 1.5 micron gate lengths, which is on the steep part of this curve. So that has implications about how you fabricate those devices. You better be able to hold the length of those gates constant. Okay, so our first circuit was going to be a 256K dynamic DRAM. And that was something that the industry was striving to do at the time. And our goal was to make this in the same technology, or a subset of the same technology we were going to use for our microprocessors, because we didn't want to have two radically different things going on in our fab. And I got to give this some background to this. My boss at the time, I'll back up for a second. When we proposed this project, we had to go to the president of the company, Hewlett-Packard, and get some extra money. And in doing that, we promised to review this program every quarter. Hewlett-Packard would fly out to here, Fort Collins, on the corporate jet, along with their entire board, and they would sit down with me and my boss and about 10 other people and say, how's it going? Which at first was not too bad. But somewhere in this program, the boss goes out to one of these corporate meetings and he says, Dana, I want you to give me a phone call when this is processed. Let me know what the yield was so I can announce it to my boss. And the phone call never came. So we built this chip. Whoops. We built this chip, and we fabricated it with marginal photolith because we didn't have our E-beam system. It has lots of process steps. We're not perfect, but we built it anyhow. It took 4 months for us to get this through the fab cycle. And when it came out, it was completely dead. It was so dead, we didn't know why it was dead. I mean, there's so many things wrong with it. So some of the things wrong were the photolith, of course, some of the etching, step coverage. The noise margin in the circuit design probably was not what it should have been. And some of the matching in a DRAM, you have to have matched parameters so a sense amp can detect a 1 or a 0. Well, all of those things were not ideal. But our ability to unravel that and figure out what was happening was not adequate. We could not figure out what to do next because multiple things were going wrong. So my boss comes back and says, well, Dana, good news. He said, we, and I appreciate forever the word we there, said, we've had a failure. That means you've got to do something different. And what I'm going to tell you about is what different we did. So we reset our entire methodology for testing and diagnosing these circuits. And I'm going to go in detail on some of these things, but I'll just go briefly through it. We instituted a unit process control, which means every sub-element of this process, inputs, outputs, and intermediaries are monitored and tested. We tracked every part, so when a part goes through a process step, we know exactly all the parameters that part has seen. We shortened the cycle time of the process. 4 months to get a part through is way too long to iterate if you have a problem. If you have a problem, start an experiment, do it again. You know, you're never going to find out what's going on, particularly since during that, in the intervening time, lots of things are going to change, so you can't hold things constant. We learned how to do flow experiments. This is where you do experiments not by starting an experiment, but by looking at random variations in your process and using them to characterize your process without actually doing an explicit experiment. We also implemented a comprehensive parameter test that told us everything about the basic elements of those circuits, and we're able to map and correlate that 7 ways to Sunday. And we, whoops. Shit. Went too far. And we redesigned the dynamic RAM. And the reason for designing the RAM, redesigning was not just to make a better circuit design, but it turns out it was better for helping us diagnose our process failures. And I'll get into that in a second. All of this dramatically improved our convergence rate on figuring out our problems and fixing them. So, you know, schematically, a process starts out with, let's say, some inputs like materials. In our case, runs through a deposition step and a masking step to define, let's say, a piece of metal on there. And you go through a number of steps like this. In our process, we had 8 masking steps. Each masking step had 1 or more depositions and 1 or more photolith steps. And each of those had sub-steps. So a metal deposition process has inputs, and I'll go give an example here. Some controls and the design of the metal machine, and outputs. So for example, the inputs might be the sputtering target, its thickness and its composition, the gases, and a whole bunch of other parameters. The controls might be the pressure sequence, the sputtering voltage, the wafer arrangement, the substrate heating, cleaning processes you used, shielding in the machine, a lot of parameters. And then there's more than just one output. The metal you get out has a thickness, a resistivity, compressive forces, adhesion, step coverage, oxidation properties, hardness, you know, a lot of things that you care about in the end product. Okay. So we instituted a unit process controls methodology. Every one of those steps, which are now a block here, every input, every intermediate, and every output is tracked, and I mean every one. And when any one of those is changed, you know it's noted. So you have a constant record of every parameter through time, and if something goes through this block at a certain date, you know what those parameters are and can later come back and do something correlations with it. So first thing we did is every one of these blocks is under process control, and there's probably 500 of them. Okay. Whoops. So now all these parameters here that used to be kind of floating around, we know we put them into we force them into the range we think that they need to be, and we know exactly what they are all the time. Second thing we did is imagine two two of these processes running in parallel. So you have one fabrication facility and another fabrication facility. And let's say they have their own sets of equipment. Well, you can take parts from one fabrication line and put it over on the other fabrication line. You can also delay parts, so you stick some parts in a certain run and just wait for a while and use those parts in a later run. What are the benefits of that? You can use that to easily cross-correlate and understand variation. When a piece of equipment, for example, changes, you can tell, okay, because parts are randomly put through either of these two lines, you can tell, for example, if a piece of equipment goes south, even if you don't know exactly what about it went south, then you can go back and track every parameter related to that piece of equipment. You can also, because of the delay here, you can shorten the effective cycle time of this process. So you want to do an experiment, you want to change a parameter, you've got things waiting here at some of these steps that you can implement a slight change while keeping everything else the same and move on. We call this part tracking. It turns out that one of the guys who was here told me that he, after this process was over, Jim Sorensen, actually made a product that they sold to other fabs in the United States to do this automatically, called Wafer Sleuth, to help find problems. So we also instituted a comprehensive test of output parameters. So we already had test patterns on our chips. Whoops, damn it. Sorry. Test patterns on our chips. The test pattern take about 6% of the surface area of the chip, measures 150 parameters. However, we started to auto-probe every die on every wafer, as opposed to just a few spots. And developed some wafer mapping, some analysis tools that you'll see here. The point here is be comprehensive. 5 minutes? Okay. So the point here is to be completely comprehensive. If you don't actually find the problem as a result of these parameter measurements, you'll at least know what the problem isn't, so you can rapidly converge on some other alternatives. We redesigned the RAM to a 4-transistor cell, which is easier to, easier to make work, but B, its failure modes can isolate whether you have, for example, a failure on first level mass, fourth level mass, because the parameters are separable. That allowed us to easily go back and understand the partial derivative of our process variables with our output variables. Let me go back for a second here. If you have an output variable that's yes, it works, or no, it doesn't work, then you're stuck with making statistical measurements through your process of the effect of something. That by definition means you're going to do many, many more iterations of that process. So if you design your experiment so it has an analog output, that intrinsically is going to improve your cycle, your convergence rate, which ultimately would be important for figuring out what technology you try to optimize. Because if it has low signal to noise to begin with, you're stuck with a very long development process. Okay, so we redid the RAM. We found out that, amazingly enough, it was better to use a redundant RAM that was 128K RAM that helped us diagnose our process than a 256K RAM, which everybody's ego wanted to do. And here, I'm going to briefly comment on the importance of understanding your goal in the program. If our goal had been to make 256K RAMs, we'd have been stuck at this point for a long time. But our goal was to make a system and a processor, and it turned out there was a better way. We also reset our circuit methodology so that we could test inside these circuits. We could access individually inside these circuits with just 4 probes through some diagnostic path. This is 1/10 of 1% of the CPU chip, of a 450,000 transistor chip. Now, under each one of these, not the big lines, not the small lines, but the little lines between the lines, is a transistor. And something might be going wrong. Imagine trying to figure out what it is if you don't have some special tools. All right. So I mentioned flow experiments. We get all our process parameters within a range by using unit process control. Then we mix and match, we randomize the wafers and look at the outputs and any parameters that are analog parameters we care about. That allows you to do correlations without wasting any time and without doing any special experiments. So you get answers in days or weeks that might have taken months or years. So here's an example of our parameter test output. This is maps of 6 out of 150 parameters, and there's actually more, but we didn't always plot these up, but these are plotted because they show one particular range. The red is bad and green is good. So the discerning among you will note that when you add up all these wafers, whoops, there's no green if you go through all the stacked levels there. So where it's good here, it's bad here. So you could think you're making progress in this because you're solving one problem, but in fact, the same wafer has a different problem somewhere else. So if till you can internalize this, you're not going to make any progress. Okay. So we had a near success. We had a lithography program. We eventually got a GCA aligner that's an optical aligner. It was pretty good. It gave line definition that looked like this. But we could not make these circuits work, try as we might, because there is just a little bit of metal left even after we over-etch these circuits. You can see down a picture now of that same optical path looking down. You can see a little webbing of standing wave problems that cause lack of the resist to bleach out. So we spent 1.5 years developing a new lithography technology that used this aligner but added some other steps. And the point here is, at some point you have to make a conscious decision to really kill a problem. And you can see this is our resultant resist, doesn't have any of these webbing problems. And you can see the breakdown voltage of our transistors went from all over the place to highly in control. And that's just one parameter. I mean, okay, so I'm going to go on. So I'm trying to quantify what the convergence rate factors did for us. We went in and deliberately reduced our cycle time from 4 months to about effectively 3/4 of a month by the staging things and shortening our intrinsic cycle time. If you have noise in your output, you can't measure whether your result is good or bad. You're not going to be able to measure the partial derivative of output versus input because there's error on the output noise. Same is true of the input. If you don't have a good measure of your parameter that you're changing, you can't measure that partial derivative very well. So you have to improve those things. And you've seen some things we did to do that. That's why all the process control is important. If you have many uncontrolled variables that essentially add, or many variables that you're changing at the same time, that essentially adds noise. So you want to try and limit your experiments to just 1 or 2 variables. Although it's theoretically possible to do a combinatorial experiment with 5 variables, if there's noise in that experiment, it's very difficult. I won't go into why. We use correlation tools to find very subtle problems, like finding a missing rectangle 1/4 micron by 1/4 micron by 1 micron in an array of 10,000 by 10,000 microns, 6 levels deep. We could find that with these tools. We could find one missing rectangle. And we did it in a week. I mean, it's like, we would never have been able to do that without some of these tools. And similarly with the mapping tools, they gave you perspectives about what was going on we never would have been able to see. And they're not very expensive to implement, but you do have to have them. Okay, so the results. Our RAM yield went from essentially nothing to about 50% in months. That allowed us to improve certainly the yield, but the biggest thing it gave us was diagnostic process feedback, because now we're dealing with 2 things: an analog output, not just 0 and 1, but how good, and also exactly what are the problems of those RAMs. You could correlate those to levels. I'm going to skip through this rapidly, but the program eventually did yield. At one point I want to make at the bottom of this, though. Although the program did yield very dramatic results and eventually was reported and claimed in various technical conferences, the product that I show you is not successful. Here's an example. Here's an example of wrong goals. And the problem with that product is it did not use standard software. So although it was the best CPU in the world and our engineers had designed the best system, it would not use the software that other people used, and consequently, there was no continuity, and the product did not sell well. This has implications in a minute, which I'll go through. We talked about technical things, but there are management and motivation things that relate to how fast you converge on a program. So I view a design project as a servo system, basically, and the goal is to have a goal and to get your team to servo to that goal. The job of the manager is to identify a doable goal, can't get there if it's not doable, and make sure the feedback loop is properly designed. And the point of this talk really is the feedback loop is essential. The feed-forward loop is important, but if the feedback loop is not properly designed, it'll take way too long to converge on whatever you're doing. And all that stuff I went through before is basically feedback loop discussion. At the bottom, I alluded to, the correct goal statement is very important. It's a servo system. If you have the right goal, your team will automatically servo to doing the right thing without any intervention on your part. You also have to be very careful to state that goal, because you're going to get that goal. You're not going to get anything else. So we did not get a high volume CPU system out of this thing, even though we had the world's best design. So for example, there's a big difference between what you're going to get if you say study cold fusion versus if you say, okay, our goal is to make a fully controllable power system. Very different approach by the design team, very different. If you go down to say, I want to make and even more different if you say, we are going to make a fully controllable power system by a certain date with high confidence. That drives an entirely different approach to how you put your team together and what you do. And even worse, as you decide to do this requires a whole another set of theory. I'm going to skip on rapidly here. So a menu for improvement in general was designed with feedback loops and comprehensive tests in mind, not just whether you're going to get your output, but how you can converge rapidly. Do all this stuff that I mentioned in previously. And that will dramatically improve your convergence rate. Probably the biggest single thing on this slide that I'm going to emphasize is the feedback loop is as important as the forward loop in your process, and usually that's an afterthought. It has to be in the foundations of what you do. And the second biggest thing is the only thing you can really afford in these technology progress is being smarter. You cannot afford more time or more money because there usually isn't not enough to paper over problems. And you've got to look for what has the greatest partial derivative of results for effort. Sometimes you can be very clever. Okay. My observation, I've only spent a year watching the LENR programs, is some things that could benefit here are shorter cycle time, better starting place, one with higher signal to noise because for reasons I've mentioned. More comprehensive low overhead tests. Think about whether you're in a near success mode. Some of these things, maybe time to break out and do something like 2-layer resist equivalent. Let me just go on. If I were working on a LENR program, I would do all those things. I would have a small co-located team with a determined leader. It's very important to have a leader who's bought into the program and is going to make it happen come hell or high water, as opposed to a guy who's going to try. Clear goals. Starting point with high, initially reasonably high signal to noise because signal to noise determines how fast you converge. Short cycle time, good tool accessibility, and ultimately something that has product value. You don't want to be working on a toy because your motivation will not be good enough. Measurable results with automation and part tracking and some specially developed tools. Ways to dice, and I didn't cover this very much, but getting close to the problem so you're not speculating about things, you're actually looking at observables. I should go back and mention, you must measure the parameter that you think is going to be important. You can't, if the one parameter is materials properties, you better be measuring everything you know about those material properties every time they change. I don't necessarily see that, and I understand there are reasons for that, but nevertheless, you will not converge unless you know that correlation. continuous flow programs. And I think, you know, a co-located staff with a modest number of people working together with the right goal could make a dramatic progress. So that's my summary. Sorry for going on.